Okay, welcome everyone. It's my pleasure to introduce Agustina Czenky, who's going to tell us about low-rank symmetric fusion categories in characteristic greater than 0. Feel free to start whenever you're ready.
Thank you. Thank you for the introduction and thank you for having me. I will be talking about some of my work in positive characteristic relating symmetric fusion categories. And before I start telling you, about what I did, I wanted to just give an overview of things that are known in positive characteristic or symmetric categories. And I'm always going to be working over an algebraically closed field. And let me assume for now that the field has characteristic 0. And we set C to be a symmetric tensor category of finite length. So this finite length condition means every object has a finite general unfolder series. And so there is a very well-known result by Deligne that kind of characterizes categories like this under a moderate growth condition. So basically what Deligne says is, if we have this moderate growth condition, then we will always get a symmetric tensor functor from our category to the category of super vector spaces. This super vector spaces category is just C2 graded vector space. So from this, because we will get this tensor functor, it means we can reconstruct our original category C with group scheme theory in super vector spaces. So more specifically, we know that C is going to be the representation category of some affine group scheme in S-Vec. And so in this sense, we say that we kind of know what the story is going to be for these symmetric tensor categories of finite length and moderate growth when we are in characteristic 0. And the question would be, will this also happen in positive characteristic? Is the story exactly the same in positive characteristic? And the answer is no. And this fails. In positive characteristic, we get examples of symmetric tensor categories that have finite length and moderate growth, but do not admit a tensor functor to super vector spaces. And I'm going to be talking about those examples, but it's, the first one would be the Berlin category in characteristic B. Does not have a functor like this for B greater than or equal to 5. So this theorem fails in positive characteristic. And I guess the question is how, what would be the analog of this? How do we change things so that something similar is still true in positive characteristic? And this is where we get this notion of incompressible. So we're going to say, let's now go to positive characteristic, and we'll say that symmetric tensor category is incompressible if any symmetric tensor functor to D is an embedding. So basically what we're saying is we cannot reconstruct incompressible categories from group schemes in a smaller symmetric category. And in characteristic 0, a supervec would be an example of an incompressible category. And in fact, in characteristic 0, vec and S-vec will be the only examples of incompressible. But in positive characteristic, we will have many more examples of these incompressible ones. And it's a recent theorem by Kulenberg of Ostrich that this moderate growth condition that we had before here will now imply that we have a symmetric tensor functor not to S-vec like we had before, but to some incompressible category of moderate growth, because now we have more examples of incompressible. And so this tensor will be to one of them. We don't really know which one, but if there will exist a tensor functor into one of them. And okay, so I guess one thing that we could also wonder is what are the incompressible categories? Because we're saying, well, we have more examples. In characteristic 0 is vec and S-vec, and in positive characteristic, we have, the Berlin categories, which are the ones that I mentioned a little while ago. We can define them as the semi-simplification of the category of tilting modules over SL2. And more generally, we are going to have ver p to the n. So I'm going to be telling you later how to explicitly define these categories, but they are nested like this, and these are all examples of incompressible categories with moderate growth and positive characteristic, and it's conjecture that they are actually all of the examples. And so if that's actually true, if these are all of the examples, then here we could just write var p to the n for some n, but we don't know. And well, another question would be, okay, so for each one of these incompressible, which categories map to it? So if I fix an incompressible category here, what are the properties of C that make it so this functor exists to that? And well, the answer in general, we don't know, but in their main theorem in a recent paper, they prove that if they add this Frobenius exact condition to the category, which has to do with a Frobenius functor that you can define on the category, then you get an equivalence with having a symmetric tensor functor to var p. So in a way, we have the answer for n equals 1 for the Berlin category, which is one of these incompressible ones. And so this is kind of what replaces the theorem that we saw at the beginning for the case of the Berlin category, which is one of these examples of incompressible. So this is what we have for the positive characteristic case. There are many questions. As you can see, it's not as simple as in the characteristic zero case where we have the theorem and we kind of know what happens here. There are many things that we don't know. And for my work, what I did was work with fusion categories. So these fusion categories are, a particular case of tensor category. So you have more conditions on the category, and that's going to make it so that many of these things that I was talking about, that I was requiring for these theorems, like finite length, moderate growth, Frobenius exact, those are always true for fusion categories. And so things get a little more simple or a little less complicated. And so let me tell you what the context is for fusion, which is just going to be a consequence of everything that we talked about. In the case of characteristic zero, the Lin's theorem says that a fusion category will have a symmetric tensor functor to the category of supervector spaces. And so we can reconstruct it as the representation category of a finite group. And because finite groups are classified, we say, okay, so we have a classification in terms of group data for symmetric fusion categories and characteristics. That is not the case for positive characteristics. So, I mean, we will have a similar reconstruction, but we cannot really say that they are classified. So in positive characteristic, well, this thing that's right here would be a consequence of this theorem, but actually Ostrich proved this before for the special case of fusion categories, that fusion categories have a symmetric tensor functor to this Berlin category. And so they can be reconstructed from finite group schemes in the Berlin category. Now, we don't really have many, they are not classified, and we also don't really have many examples of these finite group schemes in the Berlin category. So just by saying this, we are not really saying everything we can say about it, because we don't know examples, we don't know the full classification or anything. And so our question was, well, what can we say? Can we say something about classification of fusion categories? And that's kind of what the question was. Okay, so let me tell you now the definitions of these things that I've been talking about. For me, a tensor category is going to be a category that has an abelian structure, finite dimensional Hom spaces. I also have a monoidal structure, which means, well, I have a tensor product, an associativity, a unit object, and I'm always going to consider rigid categories. So everything has a dual. And also the endomorphism ring of the unit object is the field. So these are all the things that I require for a tensor
One
category.
question, Agustina, is it semi-simple or not necessarily?
No, when I add semi-simple, I'm going to be going to fusion directly.
Gotcha.
Yeah.
Thanks.
Yes. So yeah, examples of tensor categories would be vector space. I'm always going to be working with finite dimensional things, so finite dimensional vector spaces or G-graded vector spaces. So these are vector spaces that have a graduation by a group G, or representations of a group G. These are all examples of tensor categories. And well, me in my work, I work with fusion, which is these two extra conditions now. That one of them is going to be semi-simple, and the other one is going to be finitely many simple. So semi-simple is every object is going to be a direct sum of simples, and finitely many simples means we only have finitely many of these simple objects, which are the ones that don't have any non-trivial sub-objects. And so what we were interested in was classification by rank. So what can we say when the category has a low number of simple objects? So maybe what happens if the category has 2 or 3 or 4 simple objects? And let me tell you some examples of fusion. Vector spaces, that's going to be a fusion category. Then the category of representations of a group G will be fusion when G is finite. So this finite condition is so that we have finitely many simples, and this will require for semi-simple. P here is the characteristic of the field. And also the category of G-graded vector spaces, if we have G finite, that's also going to be fusion. So yeah, we were interested in looking at these fusion categories, but we also wanted them to be symmetric. So we want an extra structure on it, which is going to be a braiding. And a braiding is just a way of making objects commute in a way. So it's going to be a natural isomorphism between X tensor Y and Y tensor X. And we have to define it in such a way so that it satisfies some hexagon diagrams, which makes it coherent in the different ways in which you can be commuting these objects in the category. And if we have this structure, so if we have a category that comes with one of these braiding structures, then we can ask whether that braiding is symmetric or not. So this is going to be a property of the braiding. And it will be symmetric if when we go from X tensor Y to Y tensor X, and then back to X tensor Y using our braiding, we get the identity. And this has to be true for every X and Y in the category. And well, the examples that we've been talking about are going to be symmetric. So the category of vector spaces, where the braiding that we're considering is just commuting, well, the permutation of elements in vector spaces. Same for G-graded vector spaces, you just permute elements. And this super vector spaces category, which I said are C2 graded vector spaces. So these C2 graded vector spaces, we could either have the usual braiding, which is just permuting things, and that's what we call vex C2. And if we modify the braiding a little bit, so if instead of just doing permutation, we actually are multiplying by -1 times the degree of the elements for homogeneous elements. So this is just a little modification that we do with the braiding. Then that's what we call the category of super vector spaces. So basically, vex C2 graded vector spaces could have any of these two braidings, and those are going to be non-equivalent braided categories. And also the category of representations of a finite group, that's also going to be symmetric. And we are going to have as well this new example that appears in characteristic 0, which are the Berlinde categories. So those are also going to be symmetric. Okay, so yeah, we were wondering, okay, what can we say about classification for symmetric fusion categories? So the first thing was, well, what do we already know about classification? And like we said, we have a symmetric fusion category in positive characteristics, so the category should have a functor to this Berlinde category. But it could be that the image of that functor is maybe just vector spaces or just super vector spaces. And these two things that could happen have like special names. So we're going to say Tanakian if the functor has image on vector spaces, in which case we can reconstruct C by finite group schemes in VEC. And these are classified. So Nagata classified all finite group schemes in MEC such that the category that we get is semi-simple. So we have a classification of the symmetric fusion ones when they are Tannakian. In particular, the Berlin 2 category, so in characteristic 2 is, yes.
Sorry, a question there. For all positive P, for all positive characteristics.
Yes, because here you just need to look at, the category, like the group schemes that are in Beck, and so he can do it for any characteristic there.
Gotcha.
But also this means that all of characteristic 2 is classified, because in that case, well, everything in characteristic 2 will have a functor to Beck.
Thanks.
So it is classifying all of that, this result. And then a similar story happens when the image is super Beck. We can classify it by finite group schemes in SBEC, which was done by Masuoka for when you want this representation category to be semi-simple. And that also means we have a classification for characteristic 3 because the Berlin 3 category is the category of super Beck space. Okay, so this was, if we look at it from this perspective, but we also wanted to look at it from the perspective of rank, which is the number of simple objects. And it was proven by Etting of Austen-Beckatech that in rank 2, we only have these examples of, so they classified all of the symmetric fusion categories in rank 2 in any characteristic. Of course, this one only exists in characteristic 5, and these two exist in any characteristic. So we were wondering, okay, can we say something about rank 3 and rank 4? And we were trying to use all of these things to come up with something. Now I want to define this early in the category so that I can define verb B and verb B plus, which are the first examples in positive characteristic. And I'm going to need this semi-simplification notion. So if we have a symmetric tensor category, we can construct this new category from it that we're going to call the semi-simplification. And we call it like that because in certain cases, what we're going to get is a semi-simple category. And basically what we do is we take a look at all of the negligible morphisms in the category. So that means a morphism is negligible. If we would compose it with anything else, we take trace and we get 0. And actually, if you look at all of the negligible morphisms in the category, that's going to give you a tensor ideal. And now what we can do is quotient the category by this tensor ideal. So what does it mean? We get a new tensor category. Objects are the same as before. And home spaces, here is where we do the quotient. So we're quotienting by the negligible morphism in each home space. And so we're getting rid of everything that's negligible in the category. And this construction works for what we want because, well, this result that I have here is for a Carubian category, which is, well, it has less of a hypothesis that are fusion category that we're going to work with. But if we work with fusion, these things that you need here, those are true. And so when we do this quotient, we are going to get something semi-simple. And in particular, it also tells us what the simple objects of the quotient are, because they're going to be the images of those that were indecomposable in the original category and had non-zero dimension. So with this construction, we start with something non-semi-simple, we get rid of all negligible things, and we get something semi-simple. And that's how I'm going to define this Berlin category. So I said at the beginning, we could think of it as the semi-simplification of the category of tilting modules over SL2. And that's true, but here I have a definition that may be more approachable in a way. So they're going to give you the same category, they're equivalent, they're just constructed differently. And I believe the other one is the original one, not this one. But if we look at the cyclic group of order P, then what we can do is look at the representations of CP and do the semi-simplification construction. So we just quotient by all negligible morphisms. And that is going to be a semi-simple category. And it's going to be what we call the Berlin category. And So the validity category is the simplification of representations of CP. And this now is going to have rank P-1. So we're going to have P-1 simple objects, because before we had P in the composable objects, but LP, which is the one for S equal P here, that one has dimension 0, and so that one does not correspond to a simple object in the simplification, but all of the other ones do. And here I wrote down, well, the fusion rules, which basically means how do we multiply all of the simple objects together, and well, that's basically how it works. And let me tell you a little bit more. Like we said, when P equals 2, this just gives you vector spaces because you have only one simple object. We always have P-1 simple object. For P equals 3, we have super vector spaces. And so let's look at what happens when P is greater than or equal to 5. Well, here we can look always at the simple objects that have odd index. So we forget about all of the even ones, and we look at the abelian category generated by only odd indices. And it turns out that that's going to be a fusion subcategory. And so this is going to be a fusion category of rank P-1/2, because we have everything that's odd, and we don't have none of the even index simples. And well, some properties, this is going to be incompressible. So these are the ones that we said fail because they have no tensor functor to SVEC, which is this here. And also, it has only 4 fusion subcategories. So we have VEC and SVEC inside, and then we have this VERP plus, which is the one that has all of the odd indices, and that's it. We don't have any other subcategories in this Berlin category, and we can actually decompose it as the exterior product of the non-trivial subcategories. So it has all of these nice properties. And I wrote here an example of, well, the case for P equals 7, just to visualize what things are in this category. We said we're going to have P-1 simples. L1 here is always the unit, and then we have other 5 simples. And one thing to note is if we look at the fusion rules for these simple objects, they when you do Li times Li, you always get L1. So these are all, that's because all these are all self-dual objects. And also you can see that you always get a sum of odd things. That's why when you multiply any odd dual things, you always get a sum of odd, and that's why we get this thing is actually a subcategory. And well, I just did an example here that that's not always what happens. You don't always just get odd things. If we were to multiply L2 and L3, we would get something that's L2 plus L4. And so you can kind of know how to multiply all these things together using the fusion rules. And well, I don't know a lot about these examples that I have right here, but I still wanted to mention them. So we said we are going to have this Berlin category example, but then we could also generalize it to this verb P to the N things that we said are going to be all included like this. And basically the way that we do it is when we were constructing the Berlin category example, what we said is we quotient by the ideal of all negligible morphisms. But instead, we could look at a certain sequence of tensor ideals that are smaller than all negligible morphisms and quotient by those instead. So not get rid of everything negligible, but smaller and smaller things. And of course, the things that we're going to get will not be semi-simple because we're not getting rid of all the negligible morphisms, but we're still going to be getting categories. And that's how we define this verb P to the N. So each one corresponds to quotienting each of these tensor ideals. And I think you have to actually take abelian envelope of that, but that's kind of how the construction works. You should look at these tensor ideals, quotient, and you go from there. And these are all going to be examples of incompressible moderate with moderate growth categories. And we said, well, it's conjecture they are actually all the examples that satisfy this property. And so that's one way to construct more examples in positive characteristics. And if we want more examples, so we were saying, well, this Berlin category is the semi-simplification of the category of tilting modules of SL2. But we could just look at something that's not SL2. We could look at something else. So GN is semi-simple group, so we could look at SLN or something. And we could look instead at the tilting modules over that group. And again, do semi-simplification. And that's also, well, that's going to be an example of symmetric category positive characteristic. And well, if we wanted to have fusion, so if we wanted, for example, to have finitely many simples, then we need some condition on the Coxeter number of this group. But yeah, this is a way to construct more examples of tensor, semi-simple categories, and when it's all cases, it's going to be fusion. And like we said, well, if we take G equals SL2, that's exactly this Berlin category. Okay. So I think I'm going to be talking now about the Grothendieck ring because I want to define a morphism on it that's called the Adams operation. And basically what we were trying to look at classification of these symmetric fusion categories in positive characteristic. We wanted to use this Adams operation somehow because we knew that it was going to be giving us information that we don't have in the characteristic zero case. So let me define first this Grothendieck ring. If we have a fusion category, like we said, we have these simple objects, and we could consider the abelian group generated by all of the simple objects. And that's what our Grothendieck ring is going to be, and the multiplication in the ring is going to be induced by the multiplication, like the tensor product that we have in the category. So that's how we can construct a ring, just looking at simple objects and doing linear combinations of all of these things. And well, examples of this, if you're looking at the category of G-graded vector spaces, then the Grothendieck ring, we can identify with the group algebra of G. And if we were looking at the representations of G, then we can identify with a group of characters. So, well, it depends on the category what this Grothendieck ring is going to be. And, well, in one of the papers, Spencer, Etting of Ostrich, proved what this Grothendieck ring looks like for this Perpi plus subcategory. So this is the one that had all of the odd indices in it. And they say if we tensor it with Q, so if we rationalize it, then we have a Q algebra isomorphism with Q of C plus C minus 1, where this is a PS root of unity, P is the characteristic of the field. And in particular, this also gives us a decomposition for the Grothendieck ring of the whole category, not just the subcategory Perpi plus, using that we can decompose it as the product of these two categories. And so we wanted, and for a lot of our results, what we did was just go to the Berlin category and look at this ring and use that we knew a lot of the properties for this field. So this is a field that, well, it's very nice to work with because we're working with roots of unity. And so we can do a lot of computations there that maybe we cannot do just in general. Yeah, so this was some very nice results that we used. And now let me find the second Adams operation. So what I am going to need is to start off with the braid group. So let's think of the braid group as the group on one generator. So it's a cyclic group. And what we can do is for any object X, this is X in the category. So for any X, I can define an action from the braid group, which sends this generator, this one generator, to the braiding of X squared, like X and for X. And what's going to happen is that because our category is symmetric, doing the braiding twice, so doing this twice, is going to be the identity. So this action is actually going to factor through S2 because we can think of S2 as the braid group quotiented by, well, the squared of the generator. And so now we have an action of S2 on X squared, actually. And that's how we're going to be defining the second symmetric and second exterior powers, which kind of generalize the ones that we have in characteristic 0. And we can do it for any n. I am doing it here just for 2 because that's what I used, but you could do it for n. So the second symmetric power is going to be the maximum quotient of X squared, where this action that we just defined is trivial. And for the exterior power, it's going to be where the action factors through the sign representation. So we have these two things, second symmetric power and second exterior power, and we could define a function that for any x in the Grothendieck degree sends it to its second symmetric power minus its second exterior power. And this is going to be a ring endomorphism. And that's what we call the second AMS operation. And like we said, we don't really need n equals 2, so we could do it for any n, but if we do it for 2, then we call it second AMS operation. And so this is the thing that we wanted to use to come up with some results for classification. So let me tell you a couple of examples of what the second AMS operation looks like. So like we said, for any x, we send x to its second symmetric power minus its second exterior power. And if we're working with the category of representations of G, then, like we said, this Grothendieck ring, we can think of it as the group of characters of G. And, well, the second AMS operation will map, if you take a representation at element G, that's going to map it to the representation at G squared. So in a way, it's kind of squaring things here in this group of characters. And actually, if we were just to look at the category of G-graded vector spaces, that's exactly what it does. If we are working with the group algebra in G, it sends every G to G squared. So these are the examples that we have for this. Well, this is how the AMS operation works on the examples that we know, kind of in characteristic 0 and post characteristic. And then what happens on this new example, which is the Berlin category, and it gets a little more complicated. So it's not that anymore just squaring objects. And here I wrote a nice property that is satisfied in the Berlin category, which is, well, there's a relation between odd indices and even indices. So if we wanted to compute the second AMS operation, we would just need to do it on indices, for example. And so that's the first thing that we tried to do. Just give like a nice formula for the second AMS operation so that we could use it. And here I wrote an example of how we would compute it if we were just doing it by hand. So let's say we're in characteristic 5, so we're working with the Berlin 5 category. We have 4 symbols, L1, L2, L3, L4. And well, this is just the unit. And like we said, because of this relation we have between odd and even indices, we would just need to compute it at L3. And what we can do is just write down the fusion rules for L3 and use the fusion rules for L3 and the fact that the second AMS operation is a ring endomorphism to be able to just figure it out by equations. We know that it maps L3 to L1 minus L3 and we're done. And we could continue to be doing this by hand for p equals 7, for p equals 11. Well, but we wanted to have a formula in general, and the formula actually is that if we take any odd index symbol, then the second AMS operation maps it to the alternating sum of odd indexes. So this coincides with this. So we're just alternating +1, -1, and so on, and we break at some point. And so what we wanted to look at properties of the second-arms operation and see, well, does the second-arms operation say something about the category or not? And one thing that we started looking at, well, can the second-arms operation ever be the identity, for example? And we said, well, clearly not in Berlin. If something is fixed by the second-arms operation, then it has to be a multiple of the identity. So that was the first thing to note with this question of can it be the identity or not. Well, this remark here just says that when we mean this, we just mean objects in the category, because there are things that are fixed by the second-arms operation if we are looking at the Grothendieck ring, because there we can just take minus some symbol, which is not an actual object in the category, but it is an element in the Grothendieck ring. Yeah, so that was what we basically started thinking. Well, now that we have this formula for the second-arms operation, and we know that for any symmetric category, we have a functor into Berlinde, and the symmetric category has its operation, Berlinde has its own arms operation. How do we relate these two things? What can we, if the second-arms operation satisfies some property, does it say anything about the category? And so the first thing that we proved was if we have a non-Superdanakian, well, I should say, this non-Superdanakian condition was something that we cared about because, like we said at the beginning, Danakian and Superdanakian categories are classified. And so the ones that we care to look at are the ones that are not Superdanakian. And for those categories, we proved that if this second-arms operation to some power, let's say A and B, is the same, then we need some congruences to be satisfied mod B. And in particular, that tells us that something like this, so one power is equal to the next, can only happen when C is Superdanakian. And in particular, this also helped us prove that if C is not the category of vector spaces, so if C is non-trivial, then this could not be the identity. So this was one of the things that we really wanted to prove. It is not the identity. And I should say this fusion assumption here really is important because, well, in a recent paper, it was shown that the Lanois category, which is a semi-simple but not finite category, has this second-arms operation equal to the identity. So yeah, it is not the identity for fusion category. And so now we wanted to use all of these things also to see classification in low rank. And we looked at rank 3 and rank 4. And basically what we did is, okay, what are the options for the second-arms operation in rank 3 and rank 4, given that we know how the Grothendieck ring is, and that's how we started discarding things. And we ended up with the classification of all of rank 3 symmetric fusion categories. And for the case of rank 4, well, when you have a rank 4 fusion category, you could either have that, well, the unit is always self-dual, and so you could have the other 3 objects are self-dual as well, or these 2 are dual to each other, and this one is self-dual. And that last case is the one that we did. So the one where you have exactly 2 self-dual symbols, the one that has all symbols self-dual that we don't know. It's also open in characteristic 0. And so here I just have the list of what we end up with for every rank. And well, basically what we said is the examples are the examples that we were expecting. So there's nothing really new. It's just, well, of course, the representation categories of groups that we already know. And then these Berlinde categories and their subcategories appear, but that's basically it. So no new things. And let me just say a couple more things. So
Wait,
we
Agustina,
were
sorry, I have a question
yeah,
about notation. Would you mind going back to the previous one? What's this
yeah.
vex C4, C3?
Vex C4, C3. Oh, yes. So this is the category of C4 graded vector spaces, but it's equivariantized by C3. So here we have an action of C3 on vex C4, and then you modify the category, which is this equivariantization process. And yes, yeah,
Thank you.
this is what you get. Yeah, of course. Yeah, and this notation here also, it's just vex C4 like pointed, but you have options for this group map. Yeah, so we were trying to see if we could, because we were thinking about classification by rank, is there any relation between the rank of the category and the characteristic of the field? Like, is there anything that we can say? And yes, using this property for the Grothendieck ring that we know is isomorphic to QC plus C minus 1, we were able to prove that not super Tanakian symmetric fusion category has to have rank at least P minus 1 over 2, where P is the characteristic of the field. And this non-super Tanakian hypothesis is important because for Tanakian, it doesn't hold. Just the first examples of Tanakian that you can think of, this wouldn't be true. But for not super Tanakian, we have this lower bound. And yeah, this lower bound here is actually reached in every characteristic because we know we have this example, which is the VERP plus category, which has rank P minus 1 over 2. And so one of the questions that we wanted to answer, which we don't know, but it could be interesting, is, well, we know that an example at P minus 1 over 2 is this VERP plus category. Is it the only example? Like, is it that if the rank of the category is P minus 1 over 2, then it has to be the Berlin class category? And the answer was true for P equals 5. That was already proven by the classification of rank 2. And then we could prove it for P equals 7, but for P greater than 7, we don't know. And so that's one of the questions that we have. And another is, well, we are saying we always have this example at P minus 1 over 2. And there is a way to construct an example at P plus 3 over 2, which has to do with the link category that is constructed from the orthogonal group. And then you have to, it's kind of a more difficult construction, but it exists. So we have an example at rank P plus 3 over 2. So is there anything in the middle of those two? So are there any examples at rank P plus 1 over 2, or are those two the smallest examples we can have in rank? And of course, this here, if we are trying to finish the rank 4 classification, this could be useful because it would mean we just need to look at P equals 5 or P equals 7. So we just need to look at examples there to find this rank 4 fusion category. And we were trying to see if we could improve this bound somehow. And so we took a look at this Berlin functor, which, you know, the image could be one of its fusion subcategories. So you could either be VEC, SVEC, VERP plus, or VERP. In this case, the category will be super Tanakian, so that's already classified. And so these are the actually two options that we care about for the map. And we said, let's say that this is what happens, that the image is all of the Berlin category, then we can improve the rank. Well, the bound for the rank. And from this, we also got, well, we got some surjectivity on the Grothendieck ring. Well, we could only have these two options for a non-super Tanakian category, and also some properties for when we quotiented by Q. Yeah, so this is how we can improve this lower bound when this fiber functor we have to the Berlin category is surjective. And I think, yeah, that's it. Thank you.
Thank you so much, Agustina. Let me stop the recording.